Okay, let's look at multiplying vectors. We've looked at adding and subtracting vectors. You may know this already. This could be a nice review, and I'll be posting this on all 3 semesters worth of YouTube channels. So, multiplying vectors, people invented these definitions. Sometimes mathematicians invent stuff that physicists eventually come to go, hey, I can use that. Sometimes physicists invent some math and say, hey, we can write this more shorthand. So we're going to have 2 definitions, 2 ways of multiplying vectors that are useful. Okay? Why are they useful? Let's just take a quick look. They're called the scalar product or the dot product because we use the dot for the symbol. Could have used the cross. People use the dot, nothing deep there. Product of 2 vectors. And then there's the vector or cross product of 2 vectors. Now they're both multiplying 2 vectors. In one case I end up with a scalar. In another case I end up with a vector. Why are these useful? With the scalar product, for example, in physics, we've got mechanical work. We're going to see that right away. There's electric and magnetic flux. In fact, here you go. If you can't understand these products, you can't understand Maxwell's laws. And if you can't understand Maxwell's laws, well, you don't get to understand the electromagnetic aspect of light and a variety of things. So here it is, and understanding this will allow you to buy this t-shirt and wear it with pride. Okay, cool. So if nothing else, that's important. When we do the vector product, oops, I put this in the wrong place actually. The vector product is applicable to torque, angular momentum, magnetic force, a variety of things. So these rules are useful. Keep in mind that the useful rule, which we're going to show over here, the useful rule is written as a shorthand. So we often shorthand it. I mean, you don't need this. In fact, physics with life science folks, they're learning lots of other stuff. So they needn't bog down in this, and they often don't learn the shorthand notation, but they still use the basic definition. So fine, let's take a look at it. Scalar or dot product means that you multiply 2 vectors, you end up with a scalar, which is a number. Notice that the units are the units of A times the units of B. And that'll give you information about what the meaning is. Okay? Vector cross product is, again, the product of 2 vectors. You end up with a vector. If it's a vector, that means that you've got an amount with units. Again, the units of A times the units of B tell you what it means. And a direction. Now I've got written this RHR, or right-hand rule direction, rule C. Again, think of it as a definition. That's useful, okay, when we write our equations for physics and so on. So keep in mind here, let's get rid of this a little cluttered, that vector, any vector, can be written in terms of its components, ax I hat plus ay j hat plus az k hat. Also keep in mind that by doing this, these vectors, often called unit vectors, which I call direction vectors, this is the amount, this is the direction, the amount, the direction, everything has units. Right? Every vector can be broken up into x, y, and z parts. The magnitude of A is then just the Pythagorean theorem for 3D here. B can be written up that way too, with the magnitude that way. Also recall that the cosine of 0 is +1. The cosine of 90 degrees, or pi/2 radians, is 0. Cosine of 180 is negative. This is important. And we'll be here. Second, -1. The sine of 0 is 0. The sine of 90, or pi/2 radians, is +1. And the sine of 180 is back to 0. In fact, if you draw your unit circle, which there'll be a video on that too coming up, the sine of an angle is equal to the sine of its complementary angle, right? So the sine of 30 degrees is the same as the sine of 150, right? So that's going to be important, and you'll see why as we go along. All right, let's do that over here. Let's look at the definitions now. The definitions are scalar or dot product of 2 vectors. Now you need to just be able to toss these around. So there's not a particular way you use it. Just knowing them, you take your information and make use of it. Because there's 2 ways to write this. You can write this as, this shorthand means the magnitude of A, right? The square root of the sum of the squares of the components. Pythagorean theorem, times the magnitude of b times the cosine of theta. Every time you write a symbol, you should look at it on your picture. What does that variable mean? So theta is the angle between the lines of A and B, and I'll show you what that means. And we really use that with torque and a variety of things. It's the angle between the lines of A and B. You can also write this as the product of AX times BX plus AY times BY plus AZ times BZ. That's easy to derive. I'll show it to you in just a moment. You should be able to do it yourself once you get acquainted with it. So notice that we're just adding, and they could be positive or negative, these amounts. So when you have a vector AX I hat plus AY J hat plus AZ K hat, you can't add those amounts because they're perpendicular. Right? This length plus this length, I can't add those lengths. I can, but vectorially, the sum of those two vectors goes according to the Pythagorean theorem, right? Because they're perpendicular functions. So the surprising thing here is that, look, there's no I hat, no J hat, no K hat. This is a scalar. So don't write that. It's, we get used to writing, well, shouldn't I separate the X and Y parts? By this rule, and you'll see why, you simply multiply parallel parts. And then you actually get to add those amounts and you get some number, right? Some number with those units. All right, cool. So multiplying parallel parts is what this does well, and there's a lot of cases where we just want to multiply the parallel parts. We'll take a look at that in a second. All right, what's the basic definition for the vector product of two vectors, or the cross product, named because somebody chose to use that symbol here to distinguish those? Well, again, it's a vector. So you got two vectors, you multiply, and you get by this made-up rule, the magnitude of A times the magnitude of B times the sine of the angle between the lines of the A and B. Okay, go with that. What direction? By definition, it's the right-hand rule, or HR, right-hand rule direction, which we'll talk about some. But that's a little bit tricky to get used to. If most people were left-handed, you can bet that would be a left-handed rule by definition. It's fine. We just work it all out, and then the physics is the physics, so you're going to describe it in terms of your mathematical language. How do I do that? By components. By components, now you can write this as a determinant, and you may have learned it that way. And when you do, you may be used to having a negative in front of that first, the middle term here. When you do that, just as a heads up, and if you don't know what I'm talking about, fine, don't worry about it. The negative is here, but these guys are flipped. So it is identical to what I've written here. And as I work with you, I'll show you why I think this is an easier and faster way. This is to write this, so there's an easy way to see how to do this. Anyway, notice it's the X direction, I hat, sometimes written X hat, X, Y, Z, that's in alphabetic order. Hey, I got X, Y, Z. X, Z, Y is out of alphabetic order. And that's a negative. It's amazing how powerful this definition is, but as a definition, don't overthink it. Just go with it and you'll see it in use and it works out great. But this is the pattern. So this is Y. In alphabetic order, what comes after Y? Well, Z. And what comes after Z? Wait a minute. I've written this incorrectly. That's Y, Z. See that? I caught myself. That's Y. That's Z. That's got to be X. That's correct. And you might say X doesn't come after Z. Well, it does if you go X, Y, Z, X, Y, Z, and so on. So that's the thinking. Just go with it. Don't overthink it right now. So Y, after Y comes Z, then X. If I flip that, I've got X and Z. Okay? That was an unintentional mistake, but it helps you catch things. Wait, I can catch that. Y, Z, X, Y, X, Z, out of order, negative. Here's a Z, you can see that Z, and I have gone, after Z comes X. because we repeat the cycle, z, x, y, z minus y. Tell I was being hasty here. Z, and after z is x, so y is out of order. Okay, so just go with it and do it and pretend you know what you're doing, because you're following the rule. We'll see why it works well. So what you end up with is a vector that has a magnitude of AB sine theta. Of course, you can also take these components. These are the components. This is the big old mess for the x component of A cross B. This is the y component of A cross B. This is the z, whatever you end up with. So it's a vector with an x, y, and z component. Cool. And to get the magnitude, you can just take those, the square of each component, square root. The directions use a useful definition. We'll talk about that right-hand rule, okay? So notice, though, that when you are using the vector or cross product, it multiplies perpendicular parts. So AY is perpendicular to AZ. AZ is perpendicular to BY. AZ is perpendicular to BX, and so on. All these are perpendicular. We don't have an AX, AX, BX, BX, AX, BX, AY, BY. Review. This one multiplies parallel parts. This one multiplies perpendicular parts. Why is that useful? Obviously, people worked on things a lot and then said, hey, we can write this in a nice clean way. So let's take a look at this. If I draw two vectors, A and B, I don't know what they mean. They'll have units, and of course, you can multiply any two vectors. They may not mean anything. Of course, in physics, we'll give the meaning and application. But if this is vector A, and I can draw it here, I can draw it here, whatever, and I can move it over here. This is what I call a line of A, and this would be the line of B. Now often we'll take vectors and we'll put them tail to tail. And I did it this way just to show it not tail to tail, and then you would slide it there. What do we have here? Well, if I take the line of A and the line of B, I can see that the angle between the line of A and the line of B is here. This right here is the theta that I'm talking about. And notice, of course, it's back here too, and that's 180 degrees, so this is the complement of the angle, just simple geometry. What does it do when I take AB cos theta? Well, let's see, what's A cos theta? If I were to slide A down here, there's A, amount, direction, times the cosine of that angle. If I make that right. It's a little tricky, so you have to think about it. A times the cosine of that angle. You could look at it that way. Or do I look at it that way? Which way? It's hard to see. So pause and make sure you're looking at it. A times the cosine. Well, A has to be the hypotenuse. So in the first case, that wasn't the hypotenuse. Now that's the hypotenuse here. Times the cosine of that gives this bit right here. And so this would be A cos theta. And so I'm taking B times the part of A parallel to it. That's what this does. B times A cos theta. Now I could do that again down here, and I could say, well, I could also look at this, however I do. There's the line of A, there's the line of B. Get used to that. And I just kind of doing it. The meaning will sink in as you do problems. So sometimes you can't expect to get the meaning right away. You just got to jump in and do it, and then you'll understand as you do, which is often true with life. Okay, so where's the angle? We're the angles between the lines. So here's theta and here's theta. So now let me look at B. Again, if I slide A and B tail to tail, that's kind of nice. So there's my A, move down there. Again, sometimes we put the vector up here, and sometimes we say, hey, it's this amount in that direction. And what's B cos theta? Well, if you take a look, I can draw this, making B the hypotenuse. And so B cos theta is the part of B parallel to A. So whichever way you look at it, however intuitively you look at it, still you're multiplying parallel parts. The amount of A parallel to B times B, or the amount of B parallel to A times A. Either way, and you'll just see it in applications. So what does the other one do? Well, if I come over here and I say, wait a minute, if that's A cos theta, then A sine theta would be this. So when I do the other product, I'm multiplying B times the part of A perpendicular to it. And again, lots of uses. Don't worry, you'll see those in Stride. We're just preparing. And if I look over here and I go, hey, if that's B cos theta, then this is B sine theta. And so, yeah, the vector product, the cross product, multiplies perpendicular parts, B sine theta times A, or A sine theta times B. Okay, so just go with that and use it in Stride. Now, let's explore this a bit more, and go over here and derive these relationships using the components. So let's look at the unit vectors themselves. They're called unit vectors. Again, I prefer to call them direction vectors. They just give the direction. They don't really have a unit. They have an amount of one, but a pure one, not one of any unit at all. No units whatsoever. So the magnitude of I hat, we say, is 1. The direction is x. These two are parallel. So if you have two vectors, and they're in the same direction, the angle is 0. And so that's 1 times cosine of 0, which of course is 1. Magnitude of I hat. The same thing here. They're parallel. They each have a magnitude 1 times cosine of 0, which is 1. 1 times cosine of 0 is 1. Using that rule, multiplying parallel parts, these are parallel, but these are perpendicular. So it's a cosine of 90 degrees, and of course, however you do it, you're going to get 0. All right, let's explore that in a moment. So an important note here is that A, we say dot B, is equal to B dot A. They are the same. It doesn't matter which way you multiply them. That's not true for the vector or cross product. A cross B is AB sine theta right-hand rule. And we'll take a look at that in a moment. So I'll give you the answer one way and then need to explore the right-hand rule at some point. Think alphabetical order. Then you get the right answer and go with it and it'll sink in. X, Y, Z. I hat cross J hat equals K hat. Y, Z, X. Oops, hello. Sometimes we do use X hat and Y hat and Z hat. It doesn't matter. Just notation. Y, Z, X. Z, X, Y. They're perpendicular. The sine of the angle is the sine of 90 degrees, which is 1. Cool. Wait, these are parallel, so that's the angle 0. Sine of 0 is 0. So anytime we multiply parallel parts, we get that. Now, for various reasons, it was smart to define that B cross A is the negative of A cross B. That is, it's the same amount, but it's flipped. It's the other way. Critical for our electricity and magnetism stuff, right? That when we study electricity and magnetism, It's really important, those directions, and you know, it's just something to work through. But that tells me that, if I go j cross I, y, x is out of order, so my answer is the opposite of what I had, k cross j, and I cross k. If you notice, all these are out of order, or the flipped of the above, and so here's my y, here's my x, I need my z, but the order's flipped. Here's my z, here's my y, I need my x. And I'm thinking it through, right? I'm not just memorizing the answer. X and z, I need my y, but the order's flipped. Okay, and so just go with that for now. That's related to that right-hand rule. Okay, so that's an introduction to the meaning of this stuff. How are we doing? Okay, cool, perfect. So let's apply this unit vector stuff and derive these results. Okay, again, sometimes you just have to let go with it, because you know the first time through, it doesn't all make sense. You go through it again and it'll make sense. So how do I get this? I can do it with simple algebra. Okay, for example, what is, let's say, ax I hat dotted with b, bx I hat plus by j hat plus bz k hat. Well, I just multiply across, right? And I'm going to use this rule. So that's ax I hat dotted with bx I hat plus ax I hat dotted with by j hat plus ax I hat plus bz, or no, times bz k hat. Whew, dotted, right? Okay. Well, these are just amounts, so just realize, you know, this is just ax bx times I hat dot I hat. Now you may see the result, but I just want to show you that you can write it this way. ax by I hat dot j hat, ax bz I hat dot k hat. That product multiplies parallel parts. Those are parallel, and so that's 1. That's 0. That's 0. And so by multiplying across, again, the simple way of saying it is, hey, that multiplies parallel parts, and it gets rid of the direction vector. That's going to be ax bx. That's going to be 0 because they're perpendicular, and that's going to be 0. And so consequently, we can go through this and just go, hey, I could do this whole deal. I could say ax I hat plus ay j hat plus az k hat dotted with b, vector b in component form, by j hat plus b z k hat. And how do you multiply things like that? You just do them one by one. You take this guy, first one, multiply times that one, and times that one. And you know the only thing that's going to survive this is ax bx, but notice that the I hats go away, right? Because I hat dot I hat is a scalar product. We end up with a scalar, namely 1 in this case. So then I go and do this guy, and what does it do? That's 0, so this one's 0, 0. This guy's going to give me 0. That's going to give me ay by, and then the other guy's going to give me 0 too. And then I go through and do you can figure it out, the last one with all 3 terms, multiplying across, and that's az bz equals some number with the units of a times the units of b. All right, cool. So you could, depends on what do you do? I don't know, just use whatever you got and know that you can combine, you can set this equal to that and solve for the angle. Because if you had the components, you could do this, and you could do that with the Pythagorean theorem, and you could do that with the Pythagorean theorem, so that equals that, and then you can find the angle between those lines. Whatever. You just kind of, now you just play puzzle games, right? So now we're going to go over here real quickly and accept this definition for the directions. And there's something called permutation, means to change the order of, so I can permute these cyclically, round and round and round, or I can flip two of them and get them out of order. So here they're kind of in order, right? For you, blue, red, black, black, blue, whatever. Okay, so all right, so let's do this guy. Now let's do the same thing over here. This is a mess. We're dead. Okay, we're almost dead. Yeah, so we take the whole thing, cross this, and then you got to take each term and cross it. Now, since AXBI hat is per